In this video we're going to recap how we derived D'Alembert's equation. So remember that D'Alembert's equation is this solution to the homogeneous one-dimensional wave equation. So that's this equation here. So it's homogeneous because we've got 0 on the right hand side. This is defined for x in the real numbers, so anywhere from minus infinity to plus infinity, so this is modelling an infinitely long string, for time greater than some starting time 0. And at that starting time 0 we've got a couple of initial conditions. One of them tells us the displacement of the string u, so u at time equals 0 is given by f of x, so that's the initial shape of the string is given by f of x. And the time derivative of u, so that's the initial velocity of the string, is given by g of x, so this is again at time equals 0. So that's the problem that D'Alembert's equation solves. And D'Alembert's equation that we've seen lots of times in the lectures looks like this. So hopefully this is quite a familiar equation by now. So u of x and t is a half times f of x plus ct plus f of x minus ct, f being this function here from the initial condition, plus 1 over 2c times the integral from x minus ct to x plus ct of this function g of lambda d lambda. Okay, so how are we going to actually go about deriving D'Alembert's equation? Well, we're going to do it by introducing two theorems. So the first one will be concerned with the general solution to the wave equations without taking into account these initial conditions. And then the second one will be the application of the initial conditions to the general solution that we find from the first theorem. So the first theorem is this one here. So that theorem says that the general solution to the homogeneous wave equation, that's this guy here, is u of x and t equal to some function of x plus ct plus another function of x minus ct, where this uppercase f and uppercase g are just arbitrary real valued c2 functions. So that is they're twice differentiable, that's so that they can satisfy the wave equation, because the wave equation is defined in terms of second derivatives with respect to t and second derivatives with respect to x. And they're arbitrary, so this uppercase f and uppercase g aren't related to the lowercase f's or g's by this theorem. Okay, so how are we going to prove that? Well, the outline of the proof would be like this. First of all, we're going to factorise the wave equation, and that's going to split our problem into two problems. Both of those are going to be first order problems that we can solve using the method of characteristics. So that's the outline of the proof, but the actual specifics are like this. We say that we can rewrite utt minus c squared uxx equals 0 in this form here. So this is the operator form. So what are we doing to u in the original form of the equation? Well, we're differentiating it twice with respect to t, so we write that as d squared by dt squared. And then we're subtracting c squared multiplied by the second derivative with respect to x, so d2 by dx squared. And then all of that is what we're doing to u, and that is equal to 0. So that is just rewriting the equation in an operator form, so the operator is the bit in brackets here. And then the next step to do is to factorise that operator. Now, if you look at that operator, you can see that there are lots of squares all over the place, and there's a minus sign, so it looks like it's the difference of two squares. So we know how to factorise the difference of two squares in just general algebra, because if we have something like a squared minus b squared, then we can write that as a minus b times a plus b. So we're going to do exactly the same idea here, but in the operator setting. So we can factorise this operator as follows. We can write it as d by dt minus c d by dx, and then d by dt plus c d by dx. Okay, so that's just like what you do in algebra with factorising the difference of two squares. And so we've rewritten the equation in this factorised operator form here. Okay, so now we've factorised the wave equation. What now? Well, we've got two operators acting on u that give us 0. So we can deduce that either this first operator acting on u must give us 0, or the second operator acting on u equals 0. So in other words, if this first one gives us 0, du dt minus c du dx must be equal to 0, or if the second one gives us 0, then du dt plus c du dx is equal to 0. So we've reduced our problem now to these two problems, but these two problems are first order, they're linear partial differential equations, and they've got constant coefficients. So that sounds like something that we'll be able to solve using the method of characteristics. So let's have a go at solving them using the method of characteristics. Well, I won't go into too much details here. You can see the first video on the method of characteristics that dealt with this case where we have constant coefficients. But we can rewrite this as minus c1, so the vector minus c1, dot product with ux ut equals 0, so that's just rewriting it in a different form as a dot product of two vectors. And then this is exactly the form that we recognise to be the definition of the directional derivative. So the directional derivative of u in the direction minus c1 is equal to 0, and if a derivative is 0 in a direction, then the function must be constant in that direction. So in other words, the function u is constant in the direction minus c1, and curves, or in fact lines, that are in the direction minus c1 are defined by dx dt is equal to the coefficient of the x derivative, which was minus c, over the coefficient of the t derivative, which was 1. So just minus c over 1, which is minus c. So if we integrate both sides of that with respect to t, what do we get? We get x is equal to minus ct plus some arbitrary constant, let's call it d. And by the usual reasoning of the method of characteristics, we deduce that u must be a function, let's call it capital F, of d, in other words of the arbitrary constant. And then we can write d in terms of x and ct from our equations for the characteristic curves. So d is in fact just x plus ct. Okay, so that's the solution to problem 1. How about this second problem, problem 2? Well, that's very similar. So we can rewrite that as c, 1 dotted with ux ut equals 0. Again, this is a directional derivative equal to 0 in the direction c1, and therefore if a derivative is 0, the function itself u must be constant in that direction, so u is constant in the direction c1. And lines in the direction c1 are defined by dx dt is equal to plus c in this case, so c over 1. And if we integrate both sides of that with respect to t, what do we get? We get x is equal to ct plus some arbitrary constant, let's call it d1. And therefore, again by the usual reasoning with the method of characteristics, u must be some function, let's call it uppercase g, of that arbitrary constant. Arbitrary constant we've called d1. And using this expression that has d1 in it, we can write g of x minus ct, because d1 is x minus ct. So we've solved both of those two problems. Finally, we just have to combine them to complete the proof, because it follows from that reasoning that u of x and t is just the sum of those two solutions. So it's going to be f of x plus ct plus g of x minus ct. Okay, so that's proved that first theorem. We have found the general solution of the wave equation. So that's the general solution, but now all we need to do to find D'Alembert's formula is to apply the initial conditions in order to find what these functions that are so far arbitrary are. So this uppercase F and uppercase G we're going to find by applying the initial conditions. Okay, so the way we're going to do that is via a theorem, and we're going to prove this theorem that the solution to the problem that we started with, which is the homogeneous wave equation with the initial conditions, so in other words the Cauchy problem for the wave equation, is given by D'Alembert's equation. Okay, so let's begin the proof by saying what we already know. So we know from that theorem that we've just proved that the general solution to the wave equation is given by some function of x plus ct plus some function of x minus ct. Now all we're going to do is apply these boundary conditions, or rather initial conditions, to find out what those arbitrary functions big F and big G are in terms of our initial conditions little f and little g. So first of all, if we look at this first initial condition here, so u of x and naught is equal to little f of x. So if we put that into the general solution, that t is equal to 0, then this becomes big F of x plus big G of x, so that's this, is equal to our known function little f of x. So that's one equation. Then what about this second condition up here, that the t derivative of u evaluated when t is equal to 0 should give us g of x? Well, if we differentiate the general form of u, so that's this expression here, if we differentiate that with respect to t, first of all, because we're looking for the t derivative, then what do we get? Well, by the chain rule, there's a c in front of the t here, so we would get a c coming outside, so we'd have c times big F prime of x plus ct, but then that's evaluated when t is 0, so we just get c f prime of x. So that's where this term comes from. And then similarly, by the chain rule, we've got a minus c as the coefficient of t here, so if we're differentiating with respect to t, a minus c is going to come out, so that's this minus c here. And then we'll have g prime of x minus ct, except we're evaluating this when t is equal to 0, so we just get minus c times g prime of x. And our initial condition tells us that that expression must be equal to little g of x, where little g is the known function that represented the velocity in our initial condition. Okay, so now we're just going to do some simplification. We've got two equations for two unknown functions, f and g, so we should be able to solve these simultaneous equations to find out what big F and what big G are. So the first thing that we can do is notice that we've got expressions for F and G in this first equation and F prime and G prime in the second equation. So let's begin by differentiating this top function. So let's say that big F prime of x plus big G prime of x is equal to little f prime of x. So all we've done there is that top equation, we've differentiated both sides of it with respect to x. And this is an equation, by the way, that only depends on x. We haven't got a t anywhere here. Now, if we look at this second equation, we've got a c in front of both of the terms on the left-hand side. So let's divide this whole second equation by c. So if we get rid of the c in front of the f prime of x term and get rid of the c from here and write in a 1 over c in front of the right-hand side. So we've differentiated that top expression and we've divided the second one by c. So now we've got these two equations. What we can do is we can add them together and g prime of x will be eliminated. because if we add these together, we've got f prime of x plus f prime of x gives us 2 lots of f prime of x. If we add g prime and minus g prime, they cancel each other out. And then here we'll have f primed of x plus 1 over c g of x. Okay, so that's from adding those two equations together. What about if we subtract those two equations? Well, if we do that, then what do we end up with? Well, f prime minus f prime will give us nothing. G prime minus g prime will give us g prime plus g prime, which is 2 g prime of x. And then on the right hand side we'll have f prime of x, and this time, because we're subtracting the bottom one from the top one, we'll have minus 1 over c g of x. Okay, so we've got expressions for f prime and g prime. If we divide by 2, we're trying to find what big F and big G are. So here are those expressions divided by 2. And what we're now going to do is integrate these, because we've got expressions for f prime and g prime. We want expressions for f and g. So if we integrate them between 0 and x, then they become these expressions here. So integrating the first one, we get f of x is equal to a half times the integral of f prime, which is just f, plus 1 over c times the integral of g, plus an arbitrary constant. And similarly, integrating the second equation, g of x is equal to a half f of x minus 1 over c times the integral of g, plus some arbitrary constant. So we've introduced a couple of arbitrary constants here, a and b. But we can say something about those, because we had from the initial condition involving little f that little f was equal to big F plus big G earlier on in the proof. So now we're going to use that condition to show that a plus b must be equal to 0. And you can see that fairly straightforwardly, because if you add big F and big G, so we're adding these two lines together, here we get a half f of x plus a half f of x, which is just one lot of f of x. And then these integral terms will cancel, so that goes and that goes. And then we're left with plus a plus b. But this condition implies that we should have nothing else on this side other than f of x. So a plus b must be equal to 0. Okay, so now we've got expressions for f of x and g of x. All we need to do to complete the proof is to substitute these expressions into the general form of the solution of the wave equation that we found earlier. So what are we going to do? Well, we've got the expression for big F and big G. So wherever we see an x here, we're going to replace it with x plus ct. And wherever we see an x in the expression for g of x, we're going to replace it with an x minus ct. So that gives us a half f of x plus ct plus 1 over 2c times the integral from 0 to x plus ct of g. And then here we'll have a half f of x minus ct, that's this term here, minus 1 over 2c times the integral from 0 to x minus ct of g of lambda d lambda, plus a plus b, but we've already said that a plus b is equal to 0. Now, this integral here, remember that if you swap the limits, so changing the integral as going from 0 to x minus ct to being from x minus ct to 0, then all you do is you change the sign in front of the integral. And doing that, you can combine the two integrals together, because we've got an integral now from x minus ct to 0 plus an integral from 0 up to x plus ct. And therefore you can write it in this form, and this form is D'Alembert's formula. So that completes the proof and completes the derivation of D'Alembert's equation.